Let's talk about something really cool today. It's a tiny, tiny sensor that's basically the secret sauce inside some of the world's most precise machines. We're talking about a device that can feel a movement smaller than a human hair, and it does it over and over again without ever getting tired. So how on earth does it work? Well, we're going to find out. I mean, just think about that for a moment. If you're building a jet engine or a satellite, you need to measure tiny shifts in position, like fractions of a millimeter. So how do you even build a sensor that's accurate enough for that? And not just accurate, but also tough enough to handle all the heat and shaking that happens in a factory or on a rocket? It's a huge engineering problem, right? Well, the answer to that puzzle is this really elegant, super clever device called an LVT. Now, I know it's a bit of a mouthful, but trust me, this thing is the unsung hero in so many machines that need to be ridiculously precise.
Okay, so what exactly is this thing, and what does that complicated name even mean? Let's decode it. It's actually much simpler than it sounds.
So LVDT stands for Linear Variable Differential Transformer. At the end of the day, its job is pretty straightforward. It takes a physical movement in a straight line, engineers call this linear displacement, and it turns it into an electrical signal that a computer can actually read and make sense of. Simple as that.
The name itself is like a perfect little instruction manual. Linear just means it measures movement forwards and backwards. Variable differential, now this is the really clever bit. Its output isn't just one voltage, it's the difference between two voltages, and that's what makes it so precise. And transformer? Well, that tells you it's using the same basic physics of magnetic fields that those huge transformers on power poles use, just, on a much, much smaller scale.
All right, let's pop the hood and take a look inside. What are the pieces that make this little sensor tick?
You'd think it would be super complicated, but check this out. It's beautifully simple. You've got one coil in the middle, the primary one, that gets the power. Then on either side, you have two identical secondary coils, S1 and S2. And the only part that actually moves is this little metal core that just slides right through the middle. That's it.
So here's where the magic really happens. How does the position of that simple little core turn into a signal we can actually use? Well, it all comes down to three basic positions. First up, we've got what's called the null position. Think of this as ground zero. The core is sitting perfectly in the center, not leaning to one side or the other. Because it's perfectly balanced, the magnetic field it creates is felt equally by both secondary coils. So the voltage in the first coil, ES1, is exactly the same as the voltage in the second one, ES2. And this is where that word differential from the name comes back. The final output signal is just the difference between the two voltages, ES1 minus ES2. So, in this null position, if they're both equal, what do you get when you subtract them? You get zero, nothing. No movement means no signal. Makes perfect sense. Okay, so what happens when something actually moves? Let's say the core gets pushed a little to the left. Now it's physically closer to that first coil, S1. That means the magnetic link with S1 is stronger, so it gets more of the, magnetic juice, you could say. And now, the voltage ES1 is bigger than ES2. So, because ES1 is now bigger than ES2, when we do our little subtraction, ES1 minus ES2, we don't get zero anymore. We get a positive number. And there you have it. The device has just detected a move to the left and turned it into a positive electrical signal. How cool is that? And I'm pretty sure you can guess what happens next. If the core moves to the right, the exact opposite happens. Now it's closer to the second coil, S2. So it gets the stronger magnetic link, and its voltage, ES2, becomes bigger than ES1. And when we calculate our output again, ES1 minus ES2, we're now subtracting a bigger number from a smaller one. So what do we get? A negative number. A movement to the right creates a negative signal. This is brilliant. The LVDT doesn't just tell us that something moved, it tells us which way it went. Okay, so we've got zero for the middle, positive for one way, and negative for the other. But what does that really look like? A quick graph is going to show you exactly why this little sensor is so incredibly useful. So have a look at this chart. That horizontal line at the bottom, that's the core moving left and right. And the vertical line going up, that's the voltage we're getting out. Just look at what happens as the core moves away from the center. You get this perfectly straight, predictable line. And that straight line, that is everything. This is the crucial point. It means the output voltage is directly proportional to how far the core has moved. In simple words, move it a tiny bit, you get a tiny voltage. Move it a lot, you get a big voltage. This perfect linear relationship is exactly what makes the LVDT such a fantastic measuring tool. So,
We get how it works now. But, so what? Why should you and I care about this? Well, let's talk about where they're used, and what they're good, and maybe not so good at.
Okay, nothing's perfect, right? So let's look at the pros and cons. The biggest advantage? The moving parts don't actually touch, so there's no friction. This means it can detect the teeniest, tiniest movements, and it basically never wears out. It's also super rugged. On the downside, because it uses magnetism, it can sometimes get thrown off by other strong magnetic fields or even heavy vibrations and big temperature swings, so you have to protect it properly.
And where do you find them? Honestly, all over the place. They're used to measure movement directly, anywhere from a few millimeters to several centimeters. But they're also hooked up to other gadgets to measure things like force, weight, even pressure. Basically, the rule is, if you can make something move, an LVDT can probably measure it for you.
So, from the spinning turbines in a power plant, to the flight controls on a jet, to the robotic arms on an assembly line, this simple little transformer is just humming away silently in the background, making sure everything is perfect. So now that you know its secret, here's a question for you. Where else do you think this incredible hidden technology is shaping our world?